Welcome to this new tutorial. Today, we will be adding security measures to our DINOGROW game solidity contract using Remix and QuickNode. In previous tutorials, we have built a multi-chain mobile game that connects to Polygon, the Binance Smart Chain, and Solana. Our contract up to this point receives a transaction from the mobile game to store the score obtained in the game and the address sent by the user. If no extra security measures are provided, anyone knowing the contract address and the ABI could simply use the SaveScore function to record any score to any wallet and thus cheat the ranking. For this reason, we need to be sure to add some security measures. Since this is a mobile, decentralized game where the users have to pay for their transactions and not the contract owner, we need to maintain the user as the signer of the EVM transaction and the contract function public. We also don't have access to the user's private key, nor do we store any user data on any centralized service to perform any type of user validation. So our approach will be to set up a 32 bytes key stored in the contract that needs to be passed to the SaveScore function as a parameter. This key is set up at the moment of deployment, and it's a private field that can be changed later, but only by the contract owner. This way, we can hardcode the 32 byte key into the game so that our users can send the score, wallet, and key parameters to access the contract function, but no one else, without actually playing the game, will have a way to store any score data. Our contract so far consists of a struct user scores that will contain the last score and wallet address of the user. This struct is mapped to the user's wallet in a mapping called scores. We could have mapped the address to the score without using a struct, but in the future, we might want to map the struct user score with another address like an NFT mint address. We have a public list of addresses called users to save all the users that have previously saved scores in the contract. Our function SaveScore receives the score and the user address and is defined as external, meaning it can be called from anyone outside of the contract itself. This function simply stores the score and user address to the respective parameters of the struct keyed to the user address in the scores mapping, and it checks if the user has already entered data with this function. User exists with the user as parameter. The function user exists marked as internal view, meaning it can only be called from within the contract and will not modify any data and will return a bool. It will simply check if the user is already stored in the user's array, and if it finds any matches, it will return true. Otherwise, it will return false. So if the user exists function returns false, we save the user in the array. We will need this address in the get scores function to populate a list of all the scores saved in the contract so that the clients can see the ranking. Our function getScores doesn't receive any parameters and is marked external view, meaning it can be called by anyone outside the contract and will not modify any parameters, and will return a list of addresses, which will be our list of users, and a list of scores. So this function creates a new list of integers, all scores, the same length of the users array, and for each user in the users list, we'll get the score and save it to the all scores list in the same position. And then it will simply return both lists so that the client can see the ranking. Let's go to remix.com and open the SaveScore contract from our last tutorial. If you didn't follow along, we leave a link with the code in the description which you can copy and paste. Let's define these variables, owner and key, which we'll use now, and let's define this modifier, only owner. This will help us to filter out any interactions with the contract that are not coming from the address saved as owner wherever we want to use the modifier. So now we'll define our constructor function, which is a special function that will be called when deploying the contract. This function will require a bytes32 type key, which will be like the secret key that is needed for the SaveScore function to work, as we'll see now. So the constructor function will save the sender of the message, in this case the deployer, as the owner address, and will set the key sent as parameter as the key variable stored in the contract. We'll also create this set key function in case we wanted to update the 32 bytes key because it could have been compromised or for any other reason. This is where we will use the only owner modifier so that only the deployer of the contract can call this function and thus update the key. So all that's left for now is to update the list of parameters in our SaveScore function, because now we are going to need to receive a 32 bytes key as a parameter, and we'll simply use this require that will compare the stored key in the variable key with the key sent by the user. In case they don't match, the transaction will be reverted with an invalid key message and no info will be written to the contract. In case the user sent the exact same key, the function will proceed as expected. So let's go to our compile tab and make sure the 0.8.9 compiler is selected and hit compile. Then move to the deployments tab, make sure injected provider is selected and your MetaMask is set up with the chain you are intending to deploy to. Now to deploy, we are going to need our 32 bytes key. We'll use sionwasser.com/generate random hex to generate a random key, which we'll copy and paste. After placing a 0x prefix like you see on screen, make sure you save this safely. Much like a wallet secret key, you cannot afford to lose or expose. Hit deploy, and we can see our contract with all its functions ready. Don't forget to repeat the process with the MetaMask configured with the Binance Smart Chain to deploy to that network also. You can use the same key with the 0x prefix and hit deploy. Now let's work on our app to connect to our newly deployed contracts. Let's clone the repository of our last tutorial where we created the DINOGROW ranking. Copy the repo address, link in the description, and do git clone on an empty folder. Now let's create our .dnv file in the DINOGROW folder, and we'll create our variables for our QuickNode RPCs for the different networks we are going to connect to, and we'll create variables for the different contract addresses we are going to interact with. And let's create this EVM key variable. To store the key, we'll need to interact with our EVM contracts. Go to quicknode.com and create your endpoints for each chain if you haven't already done so. Copy and paste the addresses in their respective variables. Let's copy the addresses of our deployed contracts in their respective variables also. Make sure to use the correct deployed address for each chain. We'll use the same Solana program address from our last tutorial, and paste your hex key in the EVM key variable to have it readily available to interact with our new contracts. Let's also update the ABI. From the Deploy tab, copy the ABI and replace the contents of the ABI JSON file in the Assets folder. We are ready to update our SaveScore function. Go to the SaveScore.dart file in the Services folder, and in the SaveScore EVM function, we'll open a try catch just before asking for the gas price, so that the try part ends after sending the result. And in the catch part, we'll convert the error to string and also return it as result. We'll now add a new parameter of type uint8list called key, and we're going to send this key as the last element of the parameters list in the call contract method. Now in our main SaveScore function, for each EVM chain option, we'll read the EVM key variable from the env file and convert it to string, and then convert this to a uint8list type variable we'll call seed bytes using the hextobytes method from the Web3 Dart crypto library, which we must import. We'll send this seed bytes as the last parameter of our SafeScore EVM function. Do this for every EVM chain option. And our SafeScore function is ready. Let's try our app. If we run our app, we can see how we can send our score successfully to our contract. But let's create a temporary seed_bytes_bad variables, for which we are going to enter a wrong key, starting with 0x. If we try to send the new score, we get a transaction failed result. We can copy the result and see clearly that the transaction has been reverted with the message invalid key. We are now adding security measures to our game and hope this information has been very useful to you. Please subscribe, comment, and share. Keep on building the Web3 future.